Okay, so next up we have Brian Soden. Thanks, Brian.
Okay, thank you, Julie, and thank you for the opportunity to present this morning. I'm going to be talking about the radiative forcing from aerosol cloud interactions and just acknowledge our collaborators here, Chen Young, Ryan, Hauja, and Tristan. And I'm really just the presenter here. The one that's really done all the work is a PhD student in my group, Chen Young Park, so he really deserves the credit here. As we've heard, the radiative forcing from aerosol cloud interactions represents one of the largest source of uncertainty in estimates of historical radiative forcing. And it's defined as the change in cloud radiative effect due to aerosol-induced changes in cloud properties. For the purpose of today's talk, I'm going to modify that a little bit. I'm going to be talking specifically about the shortwave radiative effect from low clouds due to sulfate aerosols, but this is by far the dominant component of the ERFaci. You can think of the radiative forcing from aerosol cloud interactions as being consisting of two parts. Obviously, the change in aerosol concentrations is one, and then the sensitivity of the cloud radiative effect to those changes in aerosol concentrations, what's known as the susceptibility. And the real challenge in trying to determine these from observations is that there's obviously a lot of other variables that affect the cloud radiative effect besides just aerosols. So you need to control for this influence of these other weather variables. And there's a couple of ways of doing this. One is known as cloud controlling factor analysis, which uses multilinear regression against a set of variables that are known to be strongly associated with changes in low cloud properties as predictors, and then adding aerosols in as another predictor to that. Casey Wall had a nice paper a couple of years ago describing how to extend this cloud controlling factor analysis to include aerosols. And then another way that's shown to be effective is to require the changes in cloud radiative effect to actually be mediated through a change in cloud droplet number. That's also been shown to be effective in reducing the weather covariance in these relationships. And so Chen Young's idea is, well, why not incorporate both of these? And so what he did is to break that susceptibility term into two parts. One that contains the change in cloud droplet number in response to a change in aerosol concentration known as the activation rate, and then multiply that by the sensitivity of the cloud radiative effect, the cloud droplet number, and still derive these using this cloud controlling factor framework. And the nice thing about this approach is that you can actually test it using a perfect model cross-validation. And what we showed is that including the explicit inclusion of activation rate here as part of the susceptibility is really important. It reduces the error by roughly half. So it makes a big difference. So the data sets we're going to use to look at this are satellite data sets over the global oceans, 60 north to 60 south. So we have series for the cloud radiative effect, MODIS for cloud droplet number, and also as a secondary source of aerosol information, MERA2 for sulfate concentrations and the weather variables used in the cloud controlling factor analysis. And then we look at monthly anomalies from 2003 to 2023. And so if you do all this, you do the multilinear regression for each of these terms using the monthly anomalies at each grid box, and you determine these sensitivities for both the activation rate and the cloud radiative effect, multiply them together, you get this map. And you can see the numbers are largely negative, indicating that an increase in aerosol concentration causes clouds to reflect more sunlight back to space. So this is our observational estimate of the susceptibility. You can then multiply this by the change in aerosol concentrations between pre-industrial and present day. And that gives you your estimate of the effective rate of forcing between pre-industrial and present day. And you can see it's largely negative over the northern hemisphere with a global mean value of 0.32. So now we can compare this to other recent assessments of the aerosol cloud interaction, and a couple of points I want to make with this graph. One is that we've done this observational estimate both with activation explicitly included and without it, and including activation explicitly makes a big difference. So you get substantially lower estimates of the ERFaci when you include the activation, and we think that's the one that's more accurate because it does so much better on the cross-validation test. You can do it both with MODIS estimates of aerosols or MERA2. You get basically the same answer. And you can see it lies on the lower end of these observational estimates. And one of the important things there is that these dark lines represent the average estimate for the IPCC, but for the WCRP estimate, it was a highly skewed distribution towards the smaller sizes. So the black line here represents actually their best estimate of what the ERFaci is, which is very similar to the estimate we get using MERA2. So we interpret this as another piece of evidence kind of supporting this best estimate from the WCRP. It's at the low end. Now, one of the discrepancies that Isla mentioned just a minute ago is this imbalance, growing imbalance in Earth's energy supply. So we see this surplus of energy has increased over time, so it's roughly tripled over the past 20 years. And most of this is being driven by changes in the shortwave cloud radiative effect. And a number of studies have suggested that the anthropogenic reduction, or the reduction in anthropogenic aerosols over this period could be a significant contributor to this trend. So we can try to analyze this question using the same framework. We just take the observed susceptibility and multiply it by the observed trends in aerosols over this period. But when you look at the trends in aerosol concentrations over this period, you see that, yes, there have been these declines in aerosols over the northern hemisphere, but you also see very substantial increases in aerosols over the southern hemisphere, whether you look at MODIS data or MERA2, and this increase over the southern hemisphere is largely from fires over Australia and South America. And so if you take this observed susceptibility, multiply it by the trends in aerosols over this period, you get this, which is the estimate of the trend in ERFaci. You can see that there's positive forcing over the northern hemisphere due to the declining anthropogenic sulfate, but negative forcing over the southern hemisphere that almost completely offsets it. So there's this strong hemispheric asymmetry, and globally averaged, you get a value that's basically zero. So no real contribution of aerosol cloud interactions to this growing energy imbalance over this period. And we can kind of compare this observational estimate with some of the model simulations that were done as part of RFMIP. So what RFMIP did, one of the sets of simulations uses pre-industrial climatology of SSTs and then forces it in a single forcing aerosol experiment using historical projections up to 2014, and then SSP 245 after that period. And so on the left here, we have the observational estimates of the ERFaci, which are basically zero. This is the global 60 north to 60 south trend. The black shows the multi-model mean, and then these are the results for the 5 models for which we had the necessary data to look at. And you can see the models all suggest a substantially larger contribution from aerosols. So why is this? Well, you can break that global into the 2 hemispheric contrasts. You see that in the northern hemisphere, the models are showing a much larger positive forcing over this period due to the declining anthropogenic aerosols. And in the southern hemisphere, the models also have a positive forcing. And this is basically coming in large part from problems with or discrepancies between the observations and the aerosol forcing data sets post-2014 when they start using the SSP 245 projections. So just to look at that, what we've shown here are the observed sulfate concentrations for 60 north to 60 south in orange, and then northern hemisphere and southern hemisphere, and then the black lines show the multi-model mean. And you can see they agree reasonably well up through 2014, and then after that, the models diverge. And at least in the, compared to the MERA2, and you see the same thing if you look at MODIS, the SSP 245 has an exaggerated decline in sulfate over the northern hemisphere compared to what was observed. And obviously they lack information on the fires that were in the southern hemisphere. And so it's largely this kind of discrepancies in the aerosol forcing data sets, which I think, again, underscores the importance of more frequent updates in the radiative forcing data sets that we've heard a couple of times so far in this meeting. And with that, I'll just put the take-home points here, and I'm happy to answer any questions.
Thanks, Brian. Okay, any questions for Brian? Go ahead.
Thank you, Brian. In your historical or in your observational-based estimate of the historical ACI, you rely on pre-industrial sulfate aerosol concentrations. How did you derive these?
We took them from the model simulations, so we use a multi-model mean from the historical simulations for the difference in the sulfate concentrations.
Okay, thanks.
Thanks. I'm just wondering how your results compare. I think there was an issue with the Chinese emissions, which I feel like was in the opposite sense. That
yeah.
So is it from other locations?
Well, that was a very kind of localized measurement over China. Obviously, we're not looking over land here. That could be part of the discrepancy. But so we haven't been able to do like a one-to-one comparison between those two differences yet.
Any questions? I was interested in the southern hemisphere. You're saying it's from fires mainly that's missing. Is there any other possibilities that could be accounting for that southern hemisphere trends?
Well, if you look at the time series, you can see the increases in aerosols are pretty episodic, and they align pretty closely with the outbreak of fires over Australia, as well as South America. Also, you know, a contribution from Hunga Tonga as well. So yeah, the timing of those is pretty convincing that it's from fires.
We have one online.
Yeah, a question from Steve Smith asking, fire aerosols have a very different character than other anthropogenic, for example, little SO2 or mostly BCOC. If these have different ACI impacts, wouldn't that impact the results?
Yeah, so, I mean, that's a good question. We've estimated the susceptibility two ways. One, just using MERA2 sulfate at 925 millibars, so looking specifically at the sulfate concentrations. And another way, using the aerosol index from MODIS, which is obviously a column integrated, and it doesn't distinguish between different aerosol types. In terms of the energy imbalance, you'll see no difference. This is really driven by the fact that there's compensating trends in aerosols between the two hemispheres. So even if you use a much higher susceptibility, like the one you get without activation rates included, you still see almost no trend. So it's not really determined by uncertainties in the susceptibility as it is by these offsetting trends in aerosols between the hemispheres.